We'd now like to take what we've learned about phasor analysis and analyze the circuit shown here to determine the voltage Vt at the node marked here just above the 40 microfarad capacitor. As you can see, the circuit is fairly complicated, but as we work through it, you'll see that the phasor transform and analysis in the phasor domain greatly simplifies the problem. To begin though, the first thing that we look at is the frequencies of the two sources that we have, and we see that they're the same. If they were not the same, we'd have to do two separate phasor transforms on the circuit and use superposition to recombine our answers in the time domain when we're done. In this case, because they're all at the same frequency, we can just proceed with one phasor transform and then analyze it in the phasor domain and then transform it to the time domain, and we'll have our final answer. To begin, we need to take each of the elements, the sources, the resistor, the capacitors, and the inductor, and find their equivalent transform in the phasor domain. For the current source, you can see that I'm going to have a magnitude of 1/2 at an angle of 0 degrees. For the voltage source, I'm going to have a magnitude of 30√2 at an angle of 225 degrees. For the resistors just become resistors of the same magnitude, and they have 0 phase, so that'll be 50. We could put angle 0 if we want, but that's probably a bit redundant. And the 40 ohms will translate into simply 40 ohms of impedance. That leaves us with the reactive elements, the inductor and the two capacitors. Starting with the 10 millihenry inductor, our 10 millihenry inductor we know will transform into something that looks like J omega times L. And substituting for our known values, we'll have J times omega, which is 1,000, or 10 to the 3, times 10 millihenries, which is 0.01. That works out to J10. Taking the 40 microfarad capacitor now, the 40 microfarad capacitor will transform into 1 over J omega C, which is equal to, now remember, 1 over J gives us a minus J on top, divided by omega, which is 1,000, or 10 to the 3, times our capacitor value, 40 microfarads, or 40 times 10 to the minus 6, and that works out to minus J25. Our last capacitor, again, will be of the form 1 over J omega C, and of course 1 over J is simply minus J, and that will be divided by then omega, which is 10 to the 3. Notice all the omegas are the same, times 50 times 10 to the minus 6. If we do the arithmetic on that, we get minus J20. One thing to notice is that the capacitors end up with minus J, whereas the inductor ends up with plus J. Now we can gather up our elements, our capacitors, our inductor, our two resistors, and our sources, and we can redraw the circuit in the phasor domain. The nice thing about drawing the phasor domain is it's going to look just like the time domain circuit. So we'll have our current source. The arrow in here indicates the positive direction. And recall from our above analysis that the current source was a 1/2 at angle 0 degrees. The current source is in parallel with a resistor, which doesn't change values, so it's still 50 ohms. So we can put 50 down. And that's in parallel with a capacitor. Now, when we put the capacitor down, we put the capacitor symbol, and we put minus J25. You'll notice that the minus J indicates that this is a capacitor, and we also have a symbol of a capacitor, so it's somewhat redundant, but it certainly helps us keep it straight in our minds what it is we're looking at. Moving on, we've got our inductor in parallel with another capacitor, and the inductor we found was a value J10, and the capacitor down here was minus J20, and that's in series with our 40 ohm resistor. Lastly, we still have our voltage source at the end, and we'll connect that into the circuit, and that was 30 root 2 at angle 225 degrees. Now the voltage source doesn't have a polarity indicator, and so it is assumed that the top side is positive unless we're told otherwise. Recall that we're trying to find the voltage at this node here, which is now an uppercase V. When we look at the circuit, we can see that we've got two sources and 1, 2, 3, 4, 5 different elements, and so some amount of circuit analysis will have to be done. But some simplification can occur here. We can group these two impedances together and call them simply Z1, and we can group these three impedances here and call them Z2. So let's compute what Z1 and Z2 are, and that will simplify our circuit significantly. Just like when we combined resistors together, we can combine impedances together. For Z1, you can see that I'm going to have 50 in parallel with minus J 25. To calculate Z1, we have to take the inverse of the sum of the inverse of 50 ohms and minus J 25 ohms. Or recall from resistors in parallel, if I have two of them, I can take the product divided by the sum. So we'll go with the product divided by the sum. We'll have 50 times minus J 25 divided by 50 plus J. Oops, that's minus J 25 in the denominator. I can now cancel a 25 out of each term, leaving me with a 1 there, and a 2 there. And that works out then to minus J 50 over 2 minus J1. To clear the complex number from the denominator, I multiply by the complex conjugate, or 2 plus J1 divided by 2 plus J1. When I do that multiplication, I'll have minus J 50 times 2, which will give me minus J 100. And when I multiply minus J times J, gives me plus 1 times 50, gives me 50 for the real component. When I multiply complex conjugates, I will get a strictly real number on the bottom. 2 times 2 is 4, plus 1 times 1 is 1, plus 1 plus 4 gives me 5 on the bottom, so 5 out of here, leaving me 10 there and 20 there. I'm left with 10 minus J 24 Z1. For Z2 will be equal to J10, the inductor, in parallel with minus J20 plus 40 ohms for the resistor. First, we'll determine the parallel equivalent of J10 in parallel with minus J20 using the product over the sum. J10 times minus J20 divided by J10 minus J20. I can take 10 out of the numerator and the denominator out of each term, and that will leave me with, now I'll have J times minus J, which is 1, and 10 times 2 gives me 20, and in the denominator I'll have J1 minus J2, or simply minus J, plus our 40 ohms. I can rewrite that as Z2 now will be equal to 40 plus J20. I can redraw the circuit yet again to simplify it so that it's much clearer, or at this point, if you're really good at remembering things, you might choose to analyze the circuit directly, but I recommend redrawing it. So we'll redraw it one last time, where we'll still have our current source of value 1/2 at angle 0, and that will be driving an impedance which we called Z1 of value 10 minus J20, and that was in series now. That whole thing was in series with Z2, which is 40 plus J20, bringing us over to our voltage source. And connecting it back into the circuit, we'll have 30 root 2 at angle 225 degrees. Now to analyze the circuit, we can do it anywhere we want, but we're looking for this voltage here, V of t, which in the phasor domain will be simply V. And we can do it, as I said, any way we want. But with two sources, superposition looks like a good idea, so I'm going to use superposition. Well, superposition tells us that the output voltage will be equal to some function multiplied by each of the sources. So I'll have some function times 30 root 2 at angle 225 degrees, plus I'll have some other function times the current source, or 1/2 at angle 0 degrees. Returning to the voltage source, I set the other source to 0, the current source. So that's as if the current source was no longer there, or it's an open circuit. And you can see I'm going to have a voltage divider formed of 10 minus J20 divided by 10 minus J20 plus 40 plus J20. We could put brackets around those if we want, and I'll put them in a different color just so we can see where they came from. Looking now at the current source, you can see that when I set the voltage source to 0, or short it out, I'm going to end up with 10 minus J20 in parallel with 40 plus J20. If we work through the arithmetic, we're going to find that we get minus 18 plus J6 for this analysis here. And for the current source analysis, we're going to get 8 minus J6. If I add those numbers all up, you can see I'm going to get, for the real part, I'll have minus 18 plus 8 leaves me with minus 10 for the real part. And the imaginary part is J6 minus J6, or 0, is simply equal to minus 10. To determine what that is in the time domain, it probably makes sense to express it in polar form, where minus 10, if we were to plot it out on the real and the imaginary axis, is over here at minus 10. You can see that that's going to be 10 at angle plus or minus 180 degrees. So when we transform it now into the time domain, our V of t, which is what we're looking for, will have an amplitude of 10. It's always a cosine. Omega, you'll recall from the start of the question, was 1000. T plus or minus 180 degrees. And that completes the analysis.